Close your eyes for a moment, if you will, and consider where you are. Not the room you sit in, not the city beyond your window, not even the country whose borders someone once drew on a map. Consider, instead, the full and staggering truth of your actual position in the cosmos. You are riding on the surface of a ball of molten iron and silicate rock, a sphere 8,000 miles across, spinning at roughly 1,000 miles per hour at its equator, hurtling around an unremarkable star at 67,000 miles per hour, while that star itself careers around the center of a galaxy at 490,000 miles per hour, and that galaxy, our Milky Way, plunges through the intergalactic medium at over 1 million miles per hour towards something we call the Great Attractor, a gravitational anomaly so vast and so mysterious that we cannot even see it properly because it lies behind the dense star fields of our own galactic plane. You are doing all of this right now. You have been doing all of this since the moment you were born. And you have never once felt any of it. That fact alone should be enough to give you pause, to make you set down whatever you are holding, and simply marvel at the sheer improbability of your situation. But what I want to do here, in the time we have together, is something more ambitious than marveling. I want to walk you through the actual, measured, scientifically verified scale of the universe we inhabit, from the smallest distances we have ever probed to the largest structures we have ever detected, and I want to do it honestly, without flinching, without glossing over the parts that resist human intuition, because the truth is that the real scale of the cosmos is not merely large. It is not merely vast. It is something for which we genuinely have no adequate language, no evolved cognitive framework, no intuitive grasp whatsoever. And yet it is real. Every number I will share with you has been measured, checked, debated, refined, and confirmed by generations of men and women who devoted their lives to the simple and profoundly difficult act of finding out what is actually true. Let us begin where you are, with what you know, with what you can touch. Hold up your hand. Spread your fingers. The distance from the tip of your thumb to the tip of your little finger, fully outstretched, is roughly 8 inches. That is a span your brain understands intuitively. It is a human distance. You have been measuring things against your own body since infancy, and your brain is exquisitely calibrated for this range. You can estimate, with reasonable accuracy, whether a doorway is wide enough to walk through, whether a branch is close enough to grab, whether a stone is the right size to throw. These are the distances that natural selection optimized us for, the distances of survival on the African savanna, the distances of predators and prey, of watering holes and shelter, of arms and legs and the reach of a spear. Everything beyond this range, everything much larger or much smaller, requires an act of deliberate imagination, and it is precisely here that our minds begin to falter. Consider the room you are in. It is a typical room in a typical home. It is perhaps 12 feet across. You can see all of it. You understand it. Now consider the building that contains this room. Perhaps it is 50 feet tall, perhaps 100. Still manageable. Your brain has no trouble with 100 feet. You have looked up at buildings, at trees, at cliffs. Now consider the street outside, the block, the neighborhood. A mile in every direction. 6 or 7,000 people, perhaps, going about their lives within that radius. You could walk across it in 20 minutes. Your brain handles this effortlessly. It is still a human scale. But now I want you to go further, and I want you to pay close attention to the moment when your intuition begins to dissolve, because that moment is coming sooner than you think. The city you live in, or the nearest city to you, is perhaps 10 or 20 miles across. If you have ever driven across it, you have some bodily sense of that distance, the time it takes, the landmarks you pass, the way the neighborhoods change character. Now extend that to 100 miles. You can drive 100 miles in less than 2 hours on a highway. It is the distance from London to Birmingham, from New York to Philadelphia, from Tokyo to Mount Fuji. Your brain can still hold this, though it is starting to become abstract. You do not really feel 100 miles in the same way you feel the width of your hand. Now go to 1,000 miles. 1,000 miles is roughly the distance from New York to Chicago, or from London to Rome. You have perhaps flown this distance. You looked out the window of the aircraft and saw the earth sprawl beneath you. Fields, rivers, mountain ranges, cities reduced to gray smudges. At 1,000 miles, you are beginning to sense something important. The earth is large. Not incomprehensibly large, not yet, but large enough that no single human life could walk its full extent. 1,000 miles on foot, at a steady pace of 20 miles per day, would take you 50 days. Nearly 2 months of walking, sunrise to sunset, day after day, and you would still have covered only a tiny arc of the planet's surface. The circumference of the Earth is just under 25,000 miles. If you could walk at that same steady pace without stopping, without sleeping, without crossing any ocean, it would take you more than 3 years to walk around the world. But of course you cannot do this, because roughly 71% of the Earth's surface is water, deep, cold, pitiless ocean that would swallow you without a trace. The Pacific Ocean alone is so vast that it contains more surface area than all the dry land on Earth combined. You could fit every continent, every mountain range, every desert, every forest, every city that humanity has ever built, into the Pacific Ocean and still have room left over. This is not a metaphor. This is measured fact. And yet the Earth, this world that seems so large to us, this planet whose oceans we have not fully explored, whose deepest trenches we have barely visited, whose caves and forests still harbor species we have never catalogued, this Earth is, in cosmic terms, almost inconceivably small. The Earth is a sphere roughly 8,000 miles in diameter. I want you to hold that number in your mind, 8,000 miles, because we are about to start multiplying, and the numbers are going to get very large very quickly. The Moon, our closest celestial neighbor, orbits at an average distance of about 239,000 miles. That is roughly 30 Earth diameters away. If you could drive to the Moon in a car at highway speed, it would take you about 4 months of non-stop driving. The Apollo astronauts, traveling at roughly 25,000 miles per hour, made the journey in about 3 days. 3 days. That seems fast, and it is, by human standards. But the Moon is the closest thing to us. It is, in the grand scheme, right next door. It is so close that you can see it with your naked eye, that its gravitational pull raises tides in our oceans, that its reflected sunlight is bright enough to cast shadows on a clear night. And even this nearest neighbor, this companion that has orbited us for 4.5 billion years, is far enough away that you could line up every planet in the solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, between the Earth and the Moon, and still have room to spare. Every single planet. In that one gap. This is one of those facts that sounds made up but is absolutely, verifiably true, and if it startles you, good. It should, because we have barely begun. The Sun, the star around which we orbit, the thermonuclear furnace that provides every joule of energy that drives every living process on the surface of the Earth, is roughly 93 million miles away. We call this distance one astronomical unit, or AU, and it is the yardstick by which we measure everything in our solar system. Light, the fastest thing in the universe, the absolute cosmic speed limit, covers this distance in about 8 minutes and 20 seconds. This means that when you look at the Sun, which you should never do directly. You are not seeing it as it is now. You are seeing it as it was 8 minutes ago. If the sun were to suddenly vanish at this very instant, you would not know for over 8 minutes. You would continue to feel its warmth, see its light, orbit its now absent mass, for 8 minutes and 20 seconds of blissful ignorance. The sun is, in a very real sense, a memory. Everything you see in the sky is a memory. The deeper you look, the older the memory becomes. This is one of the most beautiful and unsettling truths in all of physics. To look out into space is to look back in time. Now, 93 million miles. Let us try to grasp this. If you were to drive to the sun at 60 miles per hour, 24 hours a day, it would take you about 177 years. You would not live to complete the journey. Your grandchildren would not live to complete the journey. And the sun is the nearest star to Earth. It is, by stellar standards, right here, practically touching us. The next nearest star, Proxima Centauri, a dim red dwarf in the Alpha Centauri system, is roughly 4¼ light years away. A light year is the distance light travels in 1 year, about 5.88 trillion miles. So Proxima Centauri is roughly 25 trillion miles from where you sit. If you were to drive there at 60 miles per hour, it would take you about 48 million years. The entire recorded history of human civilization, from the first scratches on cave walls to this very moment, spans perhaps 10,000 years. You would need to repeat that entire span of history nearly 5,000 times over, driving without pause, to reach the nearest star. And Proxima Centauri is our next-door neighbor. It is the porch light of the house next door. The galaxy contains hundreds of billions of other stars, most of them immeasurably farther away. But I am getting ahead of myself. Before we leave the solar system, we should appreciate what is here, because the solar system itself is vast in ways that defy ordinary comprehension. Let me walk you through it, body by body, distance by distance, and let us see how quickly the human mind begins to strain. Mercury, the innermost planet, orbits the Sun at an average distance of about 36 million miles. It is a small, dense, cratered world, scorched on one side and frozen on the other, a place of savage extremes where the temperature can swing by over 1,000 degrees Fahrenheit between day and night. Venus, shrouded in thick clouds of sulfuric acid, baking under a runaway greenhouse effect that makes its surface hotter than Mercury's, despite being farther from the Sun, orbits at about 67 million miles. Mars, the red desert that has captivated human imagination for centuries, sits at roughly 142 million miles, about 1½ AU. At its closest approach to Earth, Mars is about 34 million miles away. At its farthest, it is over 250 million miles. The distance between two planets is not fixed. It is a constantly changing quantity, a dance of orbits that never quite repeats. Beyond Mars lies the asteroid belt, a vast ring of rocky debris that most people imagine as a dense, dangerous field of tumbling boulders, the kind of thing you see in science fiction films, where spaceships must dodge and weave through a deathly hail of stone. The reality is profoundly different. The asteroid belt is mostly empty space. If you were to stand on one asteroid and look around, the nearest asteroid would likely be invisible to the naked eye, lost in the immense void. The total mass of the entire asteroid belt is less than 4% of the mass of our moon. It is not a wall. It is a whisper. Spacecraft pass through it routinely without any special precautions, because the odds of hitting anything are astronomically small, and I use that word in its most literal sense. Beyond the asteroid belt, the solar system changes character entirely. Here, in the cold outer reaches where sunlight grows thin and feeble, live the gas giants, worlds so large and so alien that they challenge our very definition of what a planet is. Jupiter, the king of planets, orbits at roughly 5 AU, about 484 million miles from the Sun. Jupiter is so large that you could fit more than 1,300 Earths inside it. Its great red spot, a storm that has been raging for at least 350 years, and possibly much longer, is itself larger than the entire Earth. Jupiter has at least 95 known moons, including 4 large ones, Io, Europa, Ganymede, and Callisto, that Galileo first spotted through his primitive telescope in 1610, forever changing our understanding of our place in the cosmos. Europa, with its subsurface ocean of liquid water beneath a crust of ice, is considered one of the most likely places in the solar system to harbor extraterrestrial life. There may be more liquid water on Europa than in all the oceans of Earth combined. And it is 790 million miles away from you, right now, orbiting a planet that makes the Earth look like a marble next to a basketball. Saturn, the ring jewel, orbits at about 9.5 AU, roughly 886 million miles. Its ring system, made of countless billions of particles of ice and rock ranging in size from grains of sugar to houses, extends more than 280,000 miles from the planet but is, in places, only about 30 feet thick. 30 feet. A ring system wider than the distance from the Earth to the Moon, thinner than a 10-story building. If you were to make a scale model of Saturn's rings using a sheet of paper, the paper would need to be about 1 kilometer wide to maintain the correct proportions. The elegance of this structure, the sheer improbability of its thinness relative to its extent, is one of the most quietly astonishing facts in planetary science. Uranus, the ice giant that rolls around the Sun on its side, its axis of rotation tilted nearly 98 degrees, probably knocked over by a colossal impact billions of years ago, orbits at about 19 AU, roughly 1.8 billion miles. Neptune, the farthest known planet, a world of supersonic methane winds, and a blue so deep it seems almost artificial, orbits at 30 AU, about 2.8 billion miles. And Neptune's distance, sunlight is 900 times dimmer than it is on Earth. Noon on Neptune would look like deep twilight here. And yet even Neptune, at the very edge of what most people consider the solar system, is not truly the edge of anything. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies that extends from about 30 AU to roughly 50 AU. Pluto, once the 9th planet and now classified as a dwarf planet, not because of any diminishment in its importance, but because we finally understood that it was one member of a vast population, orbits here, along with Eris, Makemake, Haumea, and countless thousands of other frozen worlds. And beyond the Kuiper Belt, extending outward to perhaps 50,000 AU or even 100,000 AU, lies the Oort cloud, a hypothetical sphere of trillions of icy objects that represents the true gravitational boundary of the Sun's domain. The Oort cloud has never been directly observed. It is inferred from the orbits of long-period comets that occasionally plunge into the inner solar system on trajectories that take thousands or millions of years to complete. If the Oort cloud exists as we believe it does, then the solar system is not the tidy little diagram you see in textbooks, with 8 planets orbiting in a neat disk. The true solar system is a vast, diffuse sphere, light years across, populated at its edges by trillions of frozen remnants from the birth of the Sun. Let me put this in perspective with a model, because models are the only way the human mind can approach these distances. Imagine that you shrink the Sun down to the size of a basketball. In this model, the Sun is a basketball sitting on the goal line of a football field. Mercury would be a pinhead about 10 yards away. Venus, a peppercorn 20 yards away. Earth, another peppercorn 26 yards away. Mars, a slightly smaller peppercorn, 40 yards away. Jupiter, remember, the planet that could swallow 1,300 Earths, would be a walnut, 135 yards away. That is already past the far end zone, out in the parking lot. Saturn, a large marble, 250 yards away. Uranus, a smaller marble, 500 yards away. Neptune, another small marble, 780 yards away, nearly half a mile from the basketball on the goal line. And Proxima Centauri, the nearest star? In this model, where the Sun is a basketball, Proxima Centauri would be another basketball sitting roughly 4,300 miles away. From New York to Berlin. That is the distance to the nearest star when the entire solar system, all those planets, all those billions of miles, fits within half a mile. And there are hundreds of billions of stars in our galaxy alone. This is where the human brain begins to truly struggle, and I want to acknowledge that struggle rather than pretend it away. You cannot visualize 4,300 miles. Not really. You can say the words, you can calculate the number, you can place pins on a map, but you cannot hold a distance in your mind the way you can hold the width of your hand. Your brain was not built for this. No brain was. The scale of the universe exceeds the cognitive architecture of every creature that has ever evolved on this planet, and that is not a failing of our minds. It is simply a statement about the relationship between a biological organ that evolved to navigate the savannah and a cosmos that operates on scales that have nothing to do with biological survival. But here is the beautiful thing. Even though we cannot intuitively feel these distances, we can measure them. We can calculate them. We can test our calculations against observation and find them confirmed. The human mind may not be able to viscerally comprehend 1 trillion miles, but it can absolutely prove that the number is correct. This is the quiet miracle of science, not that it makes the incomprehensible comprehensible, but that it makes the incomprehensible knowable. There is a difference. You do not need to feel a number to know it is true. Let us now leave the solar system entirely. And as we do, I want you to prepare yourself, because the jump in scale we are about to make is not incremental. It is not a gentle ramp. It is a cliff. Everything we have discussed so far, the Earth, the Moon, the Sun, Jupiter, Saturn, Neptune, the Kuiper Belt, even the vast hypothetical sphere of the Oort cloud, all of it, the entire solar system in its fullest extent, is a speck. Not a small region, not a modest neighborhood, but a speck, a mote, a single grain of sand on a beach that stretches farther than you can imagine. And I mean that almost literally. The Milky Way galaxy, our home galaxy, is a barred spiral galaxy approximately 100,000 light-years in diameter. Let me say that again, because the number deserves to be heard clearly. 100,000 light-years across. A light-year is 5.88 trillion miles. So the Milky Way is roughly 588 quadrillion miles wide. If you wrote the number out, it would be 588 quadrillion miles. 588 followed by 15 zeros. This is the distance from one side of our galaxy to the other. The Sun, our star, sits roughly 26,000 light-years from the galactic center, about 2/3 of the way out along one of the spiral arms, the Orion Arm, sometimes called the Orion Spur, a relatively minor structure between two larger spiral arms. We are not at the center of anything. We are in the suburbs, in a quiet cul-de-sac on the outskirts of a vast metropolitan structure that contains between 100 billion and 400 billion stars. Let me dwell on that number for a moment. Between 100 billion and 400 billion stars. The uncertainty in that estimate, a range of 300 billion, is itself a number so large that it defies casual comprehension. We are uncertain about the number of stars in our galaxy by an amount that exceeds the number of grains of sand on many of Earth's beaches. And every one of those stars is a sun, a thermonuclear furnace, many of them larger and brighter than ours, each one potentially orbited by its own retinue of planets, moons, asteroids, and comets. Recent data from the Kepler Space Telescope and its successor suggests that, on average, every star in the Milky Way has at least one planet. Some have many more. The total number of planets in our galaxy alone may exceed 1 trillion. 1 trillion worlds. Some of them rocky, some gaseous, some frozen, some volcanic, some with atmospheres, some without, some orbiting in the habitable zone of their star where liquid water could exist on the surface, that narrow band of orbital distance that astronomers sometimes call the Goldilocks zone, not too hot, not too cold, but just right. The Milky Way is not just large. It is old. Our galaxy formed roughly 13 billion years ago, less than 1 billion years after the Big Bang itself. In that time, it has consumed smaller galaxies, merged with others, and grown through a process of cosmic cannibalism that continues to this day. Right now, at this very moment, the Milky Way is in the process of devouring several smaller satellite galaxies, including the Sagittarius dwarf elliptical galaxy, which is being stretched and torn apart by our galaxy's gravitational tides, its stars streaming out in long, thin ribbons that wrap around the Milky Way like threads of luminous silk. In about 4.5 billion years, give or take, the Milky Way will collide and merge with the Andromeda Galaxy, our nearest large galactic neighbor, which is currently hurtling toward us at roughly 68 miles per second. When this collision happens, and it will happen, the math is settled. The two galaxies will pass to each other, their stars so widely spaced that almost none of them will actually collide, but their gravitational interaction will reshape both galaxies entirely, flinging stars into new orbits, triggering vast waves of new star formation, and eventually merging into a single, larger elliptical galaxy that astronomers have already named Milkomeda. This event will take roughly 1 billion years to complete, and if any intelligent beings are still around to watch it, the night sky will be unrecognizable. A blazing canopy of newborn stars and disrupted spiral arms stretching from horizon to horizon. But I am getting ahead of the story. Let us return to the Milky Way as it is now, today, and let us try to comprehend its structure. If you were to fly in a spaceship at the speed of light, 186,282 miles per second, the fastest speed at which anything in the universe can travel, it would take you 100,000 years to cross the Milky Way from one side to the other. 100,000 years. The entirety of recorded human history, everything from the invention of writing to the smartphone in your pocket, spans about 5,000 years. You would need to repeat that span 20 times over, traveling at the speed of light, to cross our galaxy. And during the journey, you would pass hundreds of billions of stars, each separated from its neighbors by trillions of miles of cold, dark, mostly empty space. The average distance between stars in our region of the galaxy is about 4 to 5 light years. That is roughly 25 trillion miles of nothing between each pinprick of light. Space is not crowded. Space is the very definition of emptiness, interrupted occasionally, almost reluctantly, by matter. And here is something that many people do not fully appreciate. The stars you see in the night sky, even on the clearest, darkest night, even from the top of a mountain far from any city light, represent a tiny, vanishingly small fraction of the stars in the Milky Way. On the very best night, with perfect eyesight and no light pollution, you can see roughly 4,000 to 5,000 stars with the naked eye. That sounds like a lot, And indeed the night sky can look magnificently crowded on such nights. But 5,000 stars out of 200 to 400 billion is a ratio so small that it barely registers. You are seeing 0.000002% of the galaxy's stars. And even those 5,000 visible stars are almost all within a few thousand light years of Earth. A small bubble in one arm of a galaxy that is 100,000 light years across. If the Milky Way were the size of the continental United States, the stars visible to your naked eye would occupy an area roughly the size of a small bedroom. Everything else, the vast majority of the galaxy, the billions of stars in the central bulge, the distant arms, the halo of ancient globular clusters, all of it is invisible to your unaided eye, hidden by distance, by dust, by the sheer immensity of the space between. And yet, for all its grandeur, for all its hundreds of billions of stars and trillions of planets, the Milky Way is mostly empty. If you were to randomly teleport to any location within the volume of the galaxy, the overwhelming probability is that you would find yourself in deep space. No star visible as anything more than a distant point, no planet, no moon, no asteroid, nothing but vacuum and the faint bath of cosmic radiation that pervades all of space. The matter in our galaxy, the stars, the planets, the gas clouds, the dust, accounts for a tiny fraction of its total volume. Imagine a cathedral, one of those soaring Gothic structures where the ceiling seems to reach for heaven. Now imagine the cathedral is completely empty except for a few grains of sand scattered on the floor. That is roughly the density of matter in the Milky Way. The cathedral is magnificent, but it is almost entirely air. The galaxy is magnificent, but it is almost entirely void. This emptiness is not a failure of the universe. It is its nature. The cosmos is not dense. It is spectacularly, overwhelmingly sparse. And understanding this sparseness is essential to understanding scale, because when we talk about the size of the universe, we are not talking about a space filled with things. We are talking about a space that is almost entirely nothing, punctuated here and there by islands of matter so small relative to the distances between them that calling them islands is generous. They are more like individual atoms in a vast, echoing whole. Let me take you now to the neighborhood of the Sun, because before we can appreciate the galaxy, we must first appreciate our stellar vicinity, and it is strange and marvelous in its own right. The Sun orbits the center of the Milky Way at a distance of about 26,000 light years. It takes approximately 225 to 250 million years to complete one orbit, a period sometimes called the galactic year or a cosmic year. The Sun has completed roughly 20 orbits since it was born 4.6 billion years ago. The last time the Sun was in this same approximate position in its galactic orbit, dinosaurs ruled the Earth. The time before that, the most complex life forms were primitive reptiles. The time before that, life had barely crawled out of the ocean. Every galactic year, the Earth is a fundamentally different world. The galaxy turns, slowly, patiently, and civilizations rise and fall in the blink of a cosmic eye. In the Sun's immediate neighborhood, within about 20 light years, there are roughly 50 to 60 known star systems. Some are single stars like the Sun. Many are binary or triple star systems, 2 or 3 stars locked in a gravitational embrace, orbiting each other in complex patterns. The nearest of these, as I mentioned, is the Alpha Centauri system, actually a triple star system consisting of Alpha Centauri A, a star slightly larger and brighter than the Sun, Alpha Centauri B, slightly smaller and dimmer, and Proxima Centauri, a tiny red dwarf that is the closest of the three to us at 4.24 light years. Proxima Centauri has at least one confirmed planet, Proxima Centauri b, a roughly Earth-sized world orbiting in the star's habitable zone. It may have liquid water on its surface. It may not. Proxima Centauri is a flare star, prone to violent eruptions of radiation that could strip away any atmosphere and sterilize the surface. Whether Proxima b is a potential haven for life or a blasted, irradiated wasteland is one of the great open questions in exoplanet science. Other nearby stars include Barnard Star, a red dwarf 6 light-years away that is the fastest-moving star in the sky as seen from Earth, creeping across the celestial backdrop at a rate that would be perceptible over a human lifetime if you knew exactly where to look. Sirius, the brightest star in the night sky, a brilliant blue-white beacon 8.5 light-years away, accompanied by a white dwarf companion, Sirius B. That is the compressed remnant of a star that exhausted its nuclear fuel long ago and collapsed to a size smaller than Earth while retaining a mass comparable to the Sun, and Ross 128, a quiet red dwarf about 11 light-years away that harbors a planet roughly 1.35 times the mass of Earth, orbiting close enough to its dim star to be in the habitable zone and, crucially, orbiting a star that is far less prone to violent flares than Proxima Centauri, making it one of the more promising nearby targets in the search for a world that might support life. But these are just our nearest neighbors. As we zoom out, the numbers climb rapidly. Within 100 light-years of the Sun, there are roughly 14,000 known stars. Within 1,000 light-years, the number rises to the millions. And the Sun and all its neighbors are embedded in one of the Milky Way's spiral arms, specifically the Orion Arm, a spur about 3,500 light-years across and roughly 10,000 light-years long. The Orion Arm is a relatively minor feature of the galaxy, bracketed by 2 larger arms, the Sagittarius Arm and the Perseus Arm, and the Sun sits near the inner edge of our arm, roughly between these 2 larger structures. If you have ever looked at a photograph of a spiral galaxy from above, those magnificent pinwheel structures with their sweeping arms of blue-white stars and dark lanes of dust, and wondered where we are in our own galaxy, the answer is humbling. We are in one of the small arms, in the outer suburbs, in a position that is cosmically unremarkable. There is nothing special about our location. We are not at the center. We are not on the edge. We are somewhere in between, in a perfectly ordinary neighborhood of a perfectly ordinary galaxy, and this ordinariness is itself one of the most profound discoveries in the history of human thought. There was a time, not so long ago in the span of history, when every civilization on Earth believed that it occupied the center of everything. The Earth was the fixed point around which all of creation revolved. The Sun, the Moon, the stars, the planets, the entire cosmos was a backdrop constructed for the drama of human existence. Copernicus challenged this. Galileo provided evidence. Kepler worked out the mathematics. And over the course of a few painful centuries, humanity was forced to accept a series of demotions so thorough and so relentless that they constitute what scientists sometimes call the Copernican principle, the idea that there is nothing special about our position in the universe. We are not at the center of the solar system. The solar system is not at the center of the galaxy. The galaxy is not at the center of the universe. There is, in fact, no center of the universe at all, a concept I will return to later, because it is one of the most counterintuitive and important ideas in all of cosmology. For now, let us simply note that every time humanity is assumed it occupies a privileged position, the universe has gently, firmly, and repeatedly corrected that assumption. So here we are, on an ordinary planet, orbiting an ordinary star, in the suburbs of an ordinary galaxy. And now I want to take you beyond the galaxy, out into the truly deep universe, where the scales become so large that even the Milky Way, This majestic structure containing hundreds of billions of stars, spanning 100,000 light years, shrinks to insignificance. Because the Milky Way is not alone. It is not an island in an infinite ocean. It is one galaxy among trillions, and the structures these galaxies form are the largest things that exist. The Milky Way is part of a group of galaxies called, with characteristic scientific modesty, the local group. The local group contains more than 80 known galaxies, spread across a volume roughly 10 million light-years in diameter. Most of these are small dwarf galaxies, dim, irregular collections of a few billion stars, many of them satellites orbiting the two dominant members of the group, the Milky Way and the Andromeda Galaxy. Andromeda, also known as M31, is the nearest large galaxy to our own, sitting about 2.5 million light-years away. When you look at Andromeda, and you can see it with the naked eye on a clear dark night, a faint smudge of light in the constellation that bears its name, you are seeing light that left the galaxy 2.5 million years ago, when our ancestors were just beginning to use stone tools on the plains of Africa. You are looking back in time to an era before Homo sapiens existed. Every time you glance at that faint smudge, you are performing an act of time travel so casual and so profound that it deserves a moment of reverent silence. Andromeda is slightly larger than the Milky Way, containing roughly 1 trillion stars, perhaps 2 to 3 times as many as our galaxy. It has its own system of satellite galaxies, its own spiral arms, its own central supermassive black hole. Between the Milky Way and Andromeda, in the vast gulf of intergalactic space, there is almost nothing. A few stray hydrogen atoms per cubic meter. Perhaps a handful of road stars, ejected from their home galaxies by gravitational interactions, drifting alone through the cosmic darkness with no sun to warm them, and no planetary system to call home. Intergalactic space is the emptiest environment known to science, a vacuum so thorough that it makes the space between stars within a galaxy look crowded by comparison. If you were placed in intergalactic space, far from any galaxy, and you looked around, you would see galaxies in every direction, faint smudges of light, each containing billions of stars, but you would be so far from the nearest one that your eye would perceive only darkness in most directions. You would be alone in a way that no human has ever been alone, surrounded by a void so deep and so complete that it would challenge the very concept of solitude. The local group, for all its 80-plus galaxies, is itself a small structure. It is part of a much larger assembly called the Virgo supercluster, which contains at least 100 galaxy groups and clusters spread across a volume roughly 100 million light-years in diameter. At the heart of the Virgo supercluster lies the Virgo cluster itself, a massive concentration of over 1,000 galaxies, dominated by the giant elliptical galaxy M87, a monstrous, nearly spherical collection of several trillion stars that sits at the gravitational center of the cluster like a great predator at the center of its web. M87 is famous for harboring one of the most massive black holes ever measured. A black hole with a mass of roughly 6.5 billion times that of our Sun, an object so dense that its event horizon is larger than the orbit of Neptune. In 2019, the Event Horizon Telescope collaboration produced the first direct image of this black hole, or rather, of its shadow, the dark silhouette it casts against the glowing ring of superheated matter spiraling into its maw. That image, a blurry orange ring that made front pages around the world, was a photograph of an absence, a picture of a place where space-time curves so severely that nothing, not even light, can escape. And that absence sits at the center of a galaxy that sits at the center of a cluster that is merely one node in the vast web of cosmic structure. But even the Virgo supercluster is not the largest structure we belong to. In 2014, A team of astronomers led by ridddle published a landmark paper defining a new, even larger structure, Laniakea, a supercluster of superclusters spanning roughly 500 million light-years and containing the mass of approximately 100 million billion suns. The name Mauna Kea comes from the Hawaiian words for immeasurable heaven, and it is a fitting name, because the structure is so vast that light from one end has not had time to reach the other end since the structure began to form. We are part of Mauna Kea. Our galaxy, our local group, our Virgo supercluster, all of it is a tiny filament in this immense cosmic web, drawn together by gravity into a structure that spans 500 million light-years, and yet is still just one supercluster among many. And here is where the architecture of the universe reveals itself in its most stunning form. The universe, at the largest scales, is not smooth. It is not uniform. It is structured like a sponge, or a web, or a network of soap bubbles. Galaxies are not scattered randomly through space. They are concentrated along vast filaments and sheets, like beads of dew on a spider's web, with enormous voids, regions of space hundreds of millions of light-years across that contain almost nothing between the filaments. These filaments connect galaxy clusters to one another, forming a cosmic web that spans the entire observable universe. The filaments are the densest structures, where galaxies cluster most thickly. The voids are the emptiest places in the cosmos, regions where you could travel for hundreds of millions of light-years and encounter hardly a single galaxy. The contrast is staggering. In the densest regions, thousands of galaxies crowd together in clusters millions of light-years across. In the voids, there is almost nothing at all. And yet this structure, this vast cosmic web of matter and emptiness, emerged from an almost perfectly smooth, almost perfectly uniform plasma that existed just a few 100,000 years after the Big Bang. The tiny, quantum-level fluctuations in that primordial plasma, fluctuations so small that they amounted to variations of only 1 part in 100,000, were amplified by gravity over billions of years into the web of galaxies we see today. The seeds of the largest structures in the universe were sown when the universe was smaller than a grapefruit. Let me describe some of these structures, because they are among the most magnificent things that exist. The Sloan Great Wall, discovered in 2003, is a filament of galaxies roughly 1.37 billion light-years long, one of the largest observed structures in the universe. The Hercules Corona Borealis Great Wall, detected in 2013 through the distribution of gamma-ray bursts, is estimated to be roughly 10 billion light-years across, making it the largest known structure in the observable universe. 10 billion light-years. Light from one end of this structure, traveling at 186,282 miles per second without pause, would take 10 billion years to reach the other end. That is roughly 70% of the entire age of the universe. A structure so large that even light has not had time to cross it since the cosmos began. And then there are the voids. The Bode's Void, sometimes called the Great Void, is a roughly spherical region of space about 330 million light-years in diameter that contains almost no galaxies. About 60 galaxies have been found within it, compared to the roughly 2,000 you would expect in a region that size. The Bode's Void is so empty and so vast that an astronomer named Greg Aldering once remarked that if the Milky Way were at the center of the Bode's Void, we would not have known that other galaxies existed until the 1960s. Think about that. If we lived in a slightly different part of the cosmos, the entire history of astronomy, from Galileo's first telescopic observations to Hubble's discovery of the expanding universe, would have unfolded against a backdrop of apparent nothingness. We would have looked out at the sky and seen only our own galaxy, alone in an apparently empty universe, and we might have concluded quite reasonably, that there was nothing else. The fact that we happen to live in a relatively dense part of the cosmic web, where galaxies are plentiful and observable, is a lucky accident of location that has shaped the entire trajectory of our understanding. These structures, the filaments, the walls, the voids, raise a question that is both simple and bottomless. How big is the universe? Not our galaxy, not our supercluster, not the cosmic what we can see, but the entire thing. And here is where the story takes its most fortuitous turn, because the answer depends on what we mean by the universe, and none of the answers are comforting to a mind that craves boundaries and edges. The observable universe is the portion of the total universe from which light has had time to reach us since the Big Bang, 13.8 billion years ago. You might think this means the observable universe is 13.8 billion light-years in radius. After all, the universe is 13.8 billion years old, and light travels at 1 light-year per year. But this is not correct, and the reason it is not correct is one of the most important and most commonly misunderstood facts in all of cosmology. The universe has been expanding since the Big Bang. Space itself has been stretching. The light that arrives at our telescopes today from the most distant objects we can see was emitted 13.8 billion years ago, but the objects that emitted that light have been carried away from us by the expansion of space during the time the light was in transit. As a result, those objects are now much farther away than 13.8 billion light-years. The current best estimate for the radius of the observable universe is about 46.5 billion light-years. The diameter, therefore, is about 93 billion light-years. Let me repeat that. The observable universe is roughly 93 billion light-years across. This is not a theoretical estimate. It is a measured quantity, derived from precise observations of the cosmic microwave background radiation, the distribution of galaxies, and the rate of cosmic expansion. Within this sphere 93 billion light-years across, the observable universe contains, by the best current estimates, roughly 2 trillion galaxies. 2 trillion. That is 2 million galaxies. Each of those galaxies contains, on average, roughly 100 billion stars, though the range is enormous, from dwarf galaxies with just a few million stars to giant ellipticals with several trillion. If you multiply 2 trillion galaxies by 100 billion stars per galaxy, you arrive at a number so large that it borders on the meaningless. Approximately 200 sextillion stars in the observable universe. Written out, that is 200 sextillion, a 2 followed by 23 zeros. This number is often compared to the number of grains of sand on all the beaches of Earth, and the comparison holds up surprisingly well. Various estimates put the number of sand grains on Earth's beaches at roughly 7 quintillion to 7.5 quintillion, about 7.5 times 10 to the 18th power. The number of stars in the observable universe is roughly 10,000 times larger. There are more stars in the observable universe than grains of sand on every beach on Earth, by a factor of tens of thousands. I want you to sit with that for a moment, because it is easy to let a number like 200 sextillion slide past you like water off glass. The human brain is not equipped to grasp numbers this large. We can say them. We can write them down. We can compare them to other things. But we cannot feel them. There is no visceral, gut-level understanding of what 200 sextillion means. It is simply too far outside the range of quantities that matter in everyday life. And yet this number, however incomprehensible, is a measurement. It is the result of careful observation and extrapolation, validated by multiple independent methods, and it represents our best current understanding of how many stars exist in the volume of space we can observe. The actual number of stars in the entire universe, not just the observable part, but the whole thing, which may be vastly larger, could be enormously greater. We simply do not know. The story of how we arrived at these numbers is itself one of the great intellectual adventures of the 20th and 21st centuries. For most of human history, the Milky Way was the universe. There was nothing else. The nebulae visible through telescopes were assumed to be clouds of gas within our galaxy. It was not until the 1920s that the astronomer Edwin Hubble, using the 100-inch telescope on Mount Wilson in California, measured the distance to what was then called the Andromeda Nebula and demonstrated, conclusively, that it was far too distant to be part of the Milky Way. It was, in fact, an entirely separate galaxy, an island universe, as the philosopher Immanuel Kant had speculated over a century earlier. In a single observation, Hubble expanded the known universe by a factor of roughly 100,000. The cosmos went from being a single galaxy to contain billions of them, virtually overnight. It was one of the most profound discoveries in the history of science, and it happened within living memory of people who are still alive today. Just a few years after establishing the existence of other galaxies, Hubble made an even more startling discovery. By studying the light from distant galaxies and measuring their redshift, the way their light is stretched to longer, redder wavelengths by the expansion of space, he demonstrated that nearly every galaxy in the sky is moving away from us, and that the farther away a galaxy is, the faster it is receding. This relationship, now called Hubble's law, was the observational evidence that the universe is expanding. Not that the galaxies are flying apart through space, like shrapnel from an explosion, but that space itself is expanding, carrying the galaxies along with it. Every point in the universe is moving away from every other point. There is no center to this expansion. There is no edge. Imagine the surface of a balloon being inflated. Every dot on the balloon moves away from every other dot, but no dot is at the center of the expansion, because the expansion is happening everywhere simultaneously. The universe is like that balloon, except it has one more dimension, and there is no exterior. The surface is all there is. The discovery that the universe is expanding led, inevitably, to the question, expanding from what? If you run the expansion backward in time, like rewinding a film, the galaxies converge, the distances shrink, the matter grows denser and hotter, until you reach a moment, roughly 13.8 billion years ago, when everything in the observable universe was compressed into a state of almost infinite density and temperature. This moment, this primordial singularity from which everything emerged, is what we call the Big Bang. And it is important to be precise about what the Big Bang was and was not. The Big Bang was not an explosion in space, like a bomb going off in a pre-existing room. The Big Bang was the origin of space itself. Before the Big Bang, if the word before even has meaning in the absence of time, there was no space, no time, no matter, no energy. There was nothing for an explosion to happen in. The Big Bang was the event that brought space and time into existence, and the expansion of the universe is the continued unfolding of that original event, still happening, still carrying everything apart from everything else, still stretching the fabric of space-time at every point. The evidence for the Big Bang is overwhelming and comes from multiple independent lines of observation. The expansion of the universe, first detected by Hubble, is one. The cosmic microwave background radiation, the faint, omnipresent glow of microwave light that fills all of space, the cold remnant of the hot plasma that once filled the young universe, is another. This radiation was predicted in the 1940s and accidentally discovered in 1965 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Laboratories, who initially thought the persistent hiss in their antenna was caused by pigeon droppings. The spectrum and pattern of this radiation matched the predictions of Big Bang theory with extraordinary precision, to better than 1 part in 100,000. The third great pillar of evidence is the observed abundance of light elements in the universe. The ratio of hydrogen to helium to lithium matches, to remarkable accuracy, the predictions of models that describe nuclear fusion in the first few minutes after the Big Bang, when the universe was a dense, hot soup of protons, neutrons, and electrons. These 3 lines of evidence, combined with many others, make the Big Bang the most well-supported model of cosmic origin in the history of science. But here is the thing about the Big Bang that relates most directly to our theme of scale. The Big Bang happened everywhere. It did not happen at a single point in space and then expand outward into the surrounding emptiness. There was no surrounding emptiness. The Big Bang was the origin of all space, and it happened at every point in space simultaneously. When we look at the cosmic microwave background radiation, we are looking at the afterglow of the Big Bang, but that afterglow is not located in one particular direction. It comes from every direction, equally. It surrounds us. We are inside it. We are, in a very real sense, still inside the Big Bang, because the universe that the Big Bang created is the universe we inhabit, and it has simply expanded and cooled to the point where stars and galaxies and planets and people can exist. This brings us to one of the most profound and disorienting facts about the universe. It has no center. I said this earlier, and I want to expand on it, because it is genuinely difficult to accept. Your brain insists on a center. Every explosion you have ever seen has a center. Every expanding sphere has a center. But the universe is not an expanding sphere in the ordinary sense. It is not expanding into anything. There is no outside. The expansion of the universe is not like the expansion of a cloud of gas into the surrounding atmosphere. It is the expansion of space itself, and in an expanding space that is no boundary, there is no center. Every point in the universe can equally and correctly claim to be the center of the expansion, because from every point, the expansion looks the same. Everything moves away, and the farther something is, the faster it recedes. This is not a trick of perspective. It is a fundamental property of the geometry of the universe. If an alien astronomer on a planet in the Andromeda galaxy were to study the expansion of the universe, they would see exactly the same pattern we see, everything moving away from them, as if they were at the center. And they would be right. Just as we are right. And so would an observer in any galaxy, anywhere in the observable universe. Everyone is at the center, which means no one is. I want to return now to the question of what lies beyond the observable universe, because this is where the scale of the cosmos transcends even the enormous numbers we have discussed so far. The observable universe, as I said, is about 93 billion light-years across. This is the region from which light has had time to reach us. But the total universe, the whole thing, whatever it is almost certainly much larger. How much larger? We do not know. The best we can do is set lower bounds based on the observed geometry of space. The geometry of the universe, whether it is flat, like an infinite plane, or curved, like the surface of a sphere, can be measured by studying the pattern of the cosmic microwave background radiation. These measurements, most precisely made by the Planck satellite, indicate that the universe is flat to within a very small margin of error, less than 0.5%. A perfectly flat universe is consistent with being infinite in extent. An infinite universe has no edge, no boundary, no outside. It simply goes on forever, in every direction, without end. If this is the case, and the evidence is consistent with it, then the observable universe is a tiny bubble in an infinite cosmos, a minuscule patch of a reality that extends without limit, and the 2 trillion galaxies, we can see are a vanishingly small fraction of the total number of galaxies that exist. The number of stars, the number of planets, the number of possible worlds, all of it would be infinite. Not merely large, not merely astronomical, but literally without end. Even if the universe is not infinite, the observational constraints suggest it is extraordinarily large. Some estimates, based on the flatness measurements and certain inflationary models, suggest that the total universe may be at least 250 times larger in diameter than the observable universe. If this is correct, then the total volume of the universe would be at least 15 million times larger than the volume we can observe. 15 million times. Every galaxy we have ever seen, every quasar, every supercluster, every filament and void, all of it would constitute less than 1/15 millionth of the whole. And this is a conservative lower bound. But the universe is not only vast in the direction of the large. It is equally astonishing in the direction of the small. And if the large numbers I have been sharing with you strain the limits of comprehension, the small numbers are, in their own way, even more confounding. Because when you turn your gaze inward, away from the galaxies and toward the atoms, you discover that the universe is not only immense at its largest scales, but also immense at its smallest. There are worlds within worlds within worlds, and the emptiness between things persists all the way down. Hold up your hand again. Look at it. Feel its weight, its warmth, the texture of the skin, the hardness of the bones beneath. It feels solid. It feels like something. But at the atomic level, your hand is almost entirely empty space. The atoms that make up your body, carbon, oxygen, hydrogen, nitrogen, calcium, phosphorus, and traces of dozens of other elements, are themselves mostly void. An atom consists of a tiny nucleus containing protons and neutrons, surrounded by a cloud of electrons. The nucleus is extraordinarily small relative to the size of the atom as a whole. If you were to enlarge an atom to the size of a football stadium, the nucleus would be a grain of sand at the center of the field, and the electrons would be specks of dust orbiting somewhere in the upper seats. The rest, the vast majority of the atom's volume, would be empty. Not filled with some invisible substance, not occupied by some field of force, though there are fields, but genuinely structurally empty. The solidity you feel when you press your hand against a table is not the result of matter touching matter. It is the result of electromagnetic repulsion between the electron clouds of your atoms and the electron clouds of the table's atoms. You have never actually touched anything in your life. Not in the classical sense. The atoms of your hand and the atoms of the table approach each other, but never make contact. They are separated by an electromagnetic barrier that your brain interprets as the sensation of touch. The nucleus of an atom, despite being almost inconceivably small, contains almost all of the atom's mass. A single proton has a mass of about 1.67 times 10 to the minus 27 kilograms, a number so small that writing it out in normal notation requires 26 zeros after the decimal point before you reach the first significant digit. And the proton itself is not a fundamental particle. It is composed of 3 quarks, 2 up quarks and 1 down quark, bound together by the strong nuclear force mediated by particles called gluons. The quarks and gluons are, as far as we can tell, point-like particles with no measurable internal structure. They may truly be fundamental, the bedrock of matter, with no deeper layer beneath them. Or they may be composed of something even smaller that we have not yet detected. String theory, one of the leading candidates for a theory of everything, proposes that at the very smallest scale, the Planck length, roughly 1.6 times 10 to the minus 35 meters, the fundamental constituents of matter are not particles at all, but tiny vibrating strings of energy. The Planck length is so small that it stands in relation to the diameter of an atom, as the diameter of an atom stands in relation to the entire observable universe. Imagine taking the ratio between the smallest thing you can see and the largest, and then repeating that ratio. That is the Planck length relative to ordinary experience. The scale of the subatomic world is not just small. It is structured in layers, each one revealing a new level of organization, a new set of forces and particles and interactions. Molecules are made of atoms. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. Quarks interact via gluons. And at each level, the forces that govern the interactions change. At the molecular level, it is the electromagnetic force that dominates, the force of chemical bonds, of electron sharing and transfer, of the intricate dance that produces everything from water to DNA. At the nuclear level, it is the strong force, the most powerful force in nature, capable of binding quarks together with such ferocity that it is literally impossible to isolate a single quark. The strong force is so named because it is roughly 100 times stronger than the electromagnetic force at nuclear distances. But it has an extremely short range. It operates only within the confines of the nucleus, across distances of roughly a femtometer, or 1/4,000,000,000 of a meter. Beyond that range, it drops to zero. This is why nuclei are small. The strong force can hold things together, but only within a tiny volume. Make the nucleus too large, and the electromagnetic repulsion between the protons, which does not have a range limit, overwhelms the strong force, and the nucleus becomes unstable. This is the fundamental reason why heavy elements are radioactive. Their nuclei are simply too large for the strong force to hold together indefinitely. Then, there is the weak nuclear force, responsible for certain types of radioactive decay, and for the nuclear reactions that power the sun. The weak force is weaker than both the electromagnetic force and the strong force, and it has an even shorter range, only about 1,000th the diameter of a proton. And finally, there is gravity, the weakest of the four fundamental forces, by an almost comical margin. Gravity is roughly 10 to the 39 times weaker than the strong force. That is a 1 followed by 39 zeros. To put this in perspective, when you pick up a paper clip with a small refrigerator magnet, the electromagnetic force of that tiny magnet is overcoming the gravitational pull of the entire Earth. The entire planet, all 6 sextillion metric tons of it, pulling downward, and a magnet the size of your thumbnail overcoming that pull with ease. Gravity is so weak at the quantum scale that it plays essentially no role in the interactions of particles. And yet, on the scale of planets, stars, and galaxies, gravity is the dominant force, the architect of all cosmic structure. This is because gravity, unlike the strong and weak forces, has infinite range, and because it is always attractive. It always pulls things together, never pushes them apart. Over vast distances and vast amounts of mass, those tiny individual pulls add up to an unstoppable force that shapes the entire universe. The interplay of these four forces, gravity, electromagnetism, the strong force, and the weak force, produces everything we see. Every star, every planet, every atom, every ray of light, every thought in your mind, every beat of your heart is the result of these four forces acting on matter according to the laws of quantum mechanics and general relativity. Four forces. That is all. The entire dizzying complexity of the universe, from the spiral arms of galaxies to the structure of a snowflake to the firing of a neuron, emerges from the interactions of four fundamental forces acting on a handful of elementary particles. The elegance of this is breathtaking. The fact that such complexity can arise from such simplicity is, to my mind, one of the most beautiful things about the universe. But the atomic world holds another surprise, and it is one that relates directly to the question of scale. The atoms in your body are old. Not merely old in human terms, not merely old in geological terms, but old in cosmic terms. The hydrogen atoms in your body, and roughly 60% of the atoms in your body are hydrogen, were formed in the first few minutes after the Big Bang, 13.8 billion years ago. They are as old as the universe itself. They have been through everything. They were part of the primordial gas that filled the young cosmos. They drifted through space for millions of years. They were pulled by gravity into clouds that collapsed into the first stars. Some of them were fused in those first stars into heavier elements: helium, carbon, oxygen, iron. When those first stars died, some in the slow, graceful exhalation of a planetary nebula, some in the cataclysmic detonation of a supernova, they scattered their enriched material back into space, seeding the interstellar medium with the elements that would eventually form new stars, new planets, and new life. The carbon in your muscles, the calcium in your bones, the iron in your blood, the phosphorus in your DNA, all of it was forged inside a star that died before the sun was born. You are, as Carl Sagan so memorably put it, star stuff. You are the universe experiencing itself, a collection of atoms that were once scattered across light years of interstellar space, and that have come together, temporarily and improbably, to form a being that can contemplate its own origins. This is not poetry. It is chemistry. The nucleosynthetic origin of the elements is one of the best understood processes in astrophysics. We know which elements are made in which types of stars. We know that hydrogen and helium were made in the Big Bang. We know that carbon, nitrogen, and oxygen are made in the cores of massive stars through a process called the CNO cycle. We know that elements heavier than iron, gold, silver, platinum, uranium, are made in the most violent events in the universe, supernovae and neutron star mergers, where temperatures and pressures are so extreme that atomic nuclei are slammed together with enough force to overcome the electromagnetic repulsion and fuse into heavier elements. The gold in a wedding ring was likely forged in the collision of two neutron stars, objects so dense that a teaspoon of their material would weigh 1 billion tons, in an event that occurred billions of years ago, in a galaxy that may no longer exist. The atoms traveled through space, were incorporated into the cloud of gas and dust that collapsed to form our solar system, settled into the crust of the young Earth, and were eventually mined by human hands. The journey of a single gold atom, from neutron star collision to ring finger, is a saga that spans billions of years and billions of light years, and it is happening, right now, in the matter that composes every object you can see. Let me bring this back to scale, because scale is our theme, and the atomic world provides some of the most staggering numbers of all. A single drop of water, a drop small enough to balance on the tip of your finger, contains approximately 1.67 sextillion molecules of water. That is 1/670 quintillion molecules. Each of those molecules consists of 3 atoms, 2 hydrogen and 1 oxygen. So the tiny drop contains roughly 5 sextillion atoms. If you could somehow count atoms at a rate of 1 per second, it would take you about 158 trillion years to count all the atoms in a single drop of water. The age of the universe is 13.8 billion years. You would need to wait roughly 11,000 times the current age of the universe to finish counting. And this is 1 drop of water. The number of atoms in your body is roughly 7 octillion, a 7 followed by 27 zeros. The number of atoms in the Earth is approximately 1.33 times 10 to the 50th power. The number of atoms in the observable universe is estimated at roughly 10 to the 80th power, a 1 followed by 80 zeros. These numbers are so far beyond human intuition that they exist purely in the realm of mathematics. They can be written down and manipulated algebraically, but they cannot be imagined. No mind, human or otherwise, has ever visualized 10 to the 80th of anything. And now I want to turn to time, because the scale of the universe is not only spatial, it is temporal. The universe is not only vast in extent but vast in duration, and the history of the cosmos, like its geography, exceeds our intuitive grasp by many orders of magnitude. The universe is 13.8 billion years old. That number, like the spatial distances we have discussed, is precise, not a rough estimate, not a philosophical guess, but a measured value with an uncertainty of only about 1%. It is derived from multiple independent lines of evidence: the expansion rate of the universe, the temperature and spectrum of the cosmic microwave background, the ages of the oldest known stars, and the abundances of the lightest elements. All of these methods converge on the same answer: 13.8 billion years, give or take about 40 million. In the history of science, few quantities of such fundamental importance have been determined with such precision. But what does 13.8 billion years mean? How can we grasp a duration this long? One of the most effective techniques is compression, taking the entire history of the universe and compressing it into a more manageable timescale. Carl Sagan popularized this approach with his cosmic calendar, in which the entire 13.8 billion year history of the universe is compressed into a single calendar year. In this scheme, the Big Bang occurs at midnight on January 1st. Each month represents roughly 1.15 billion years. Each day represents roughly 38 million years. Each second represents roughly 438 years. On this cosmic calendar, the Milky Way forms around March 16th. Our Sun and solar system do not appear until September 2nd. The universe was already 2/3 of its current age before our star was born. The oldest known fossils of single-celled life on Earth appear around September 21st. Complex multicellular life does not emerge until December 5th. The Cambrian explosion, that sudden riot of animal evolution that produced the ancestors of nearly all modern animal phyla, occurs around December 17th. Dinosaurs appear on December 25th, Christmas Day, and go extinct on December 30th. The entire history of the genus Homo, every species of human that has ever lived, from Homo habilis to Homo sapiens, occupies the last few hours of December 31st. Recorded human history, writing, cities, empires, science, technology, everything we typically call civilization, begins at roughly 11:59 and 46 seconds p.m. on December 31st, 14 seconds before midnight. The Industrial Revolution, the discovery of electricity, the invention of the telephone, both world wars, the moon landing, the internet, and everything that has happened in the 21st century all occur in the last fraction of a second. If you blink at midnight, you will miss all of human history. This is not a metaphor designed to make you feel small, although it does have that effect. It is an accurate representation of the relative timescales involved. The universe has existed for an enormously long time, and life as we know it is a very recent development. Intelligent life, the kind that builds telescopes and asks questions about the cosmos, is so recent as to be essentially instantaneous on the cosmic timescale. If the universe were a person, 70 years old, human civilization would have existed for less than 1,000th of a second of that person's life. But the story of cosmic time is not just about the past. It is also about the future. And the future of the universe, as best we can determine from current physics, is unimaginably long, so long that the 13.8 billion years that have already elapsed are a negligible fraction of what is to come. The age of stars, the era in which nuclear fusion lights up the cosmos, in which galaxies shine and planets are warmed by their suns, is a brief chapter in a much longer story. Stars will continue to form for perhaps another 100 trillion years, though the rate of star formation is already declining and will continue to slow as the raw material, gas and dust, is consumed. Eventually, the last star will exhaust its fuel, the last nuclear furnace will dutter and die, and the universe will enter what physicists call the degenerate era, a vast, dark epoch dominated by the cooling remnants of dead stars, white dwarfs, neutron stars, and black holes. White dwarfs, the dense cores left behind when stars like our Sun die, will cool slowly over trillions of years, radiating away their residual heat until they become cold, dark objects known as black dwarfs. No black dwarf exists yet. The universe is not old enough for any white dwarf to have cooled completely. The time required for a white dwarf to cool to the temperature of the cosmic microwave background is estimated to be on the order of a quadrillion years, roughly 100 times the current age of the universe. The first black dwarfs will not appear for trillions of years. And even after the last white dwarf goes dark, the universe will still exist. It will simply be dark. The black holes will remain, slowly evaporating through a quantum process called Hawking radiation, losing mass particle by particle over timescales that make everything we have discussed so far look like the blink of an eye. A stellar mass black hole, one with a mass of perhaps 10 times the Sun, would take roughly 10 to the 67 power years to evaporate. That is a 1 followed by 67 zeros. The supermassive black holes at the centers of galaxies, with masses of billions of suns, would take even longer, perhaps 10 to the 100 power years, a number called the googol. And after the last black hole evaporates, the universe will enter its final state, the dark era, an eternity of cooling, expanding, increasingly dilute space, populated only by a thin gruel of electrons, positrons, neutrinos, and photons, drifting apart in a void that grows ever larger and ever colder, approaching but never quite reaching absolute zero. This is the heat death of the universe, not a dramatic conflagration but a slow, quiet fade into the deepest possible stillness. And it will last forever. Or at least, it will last as close to forever as physics allows. The timescales of the future universe are genuinely numbing. To say that the current age of the universe is negligible compared to its future lifespan is an understatement, so severe that language cannot adequately convey it. Imagine that the current age of the universe, 13.8 billion years, is represented by a single step, one pace forward. On that scale, the time until the last star dies would be a walk around the Earth. The time until the last white dwarf cools to a black dwarf would be a walk to the nearest star. And the time until the last supermassive black hole evaporates would require a number of steps so large that there is no physical object in the universe to compare it to. The number exceeds the number of atoms in the observable universe by a factor so vast that even the number of digits in the number is incomprehensibly large. This is the temporal scale of the cosmos. We exist in the first eye blink of an essentially eternal universe. The age of stars, the era of light and warmth and life, is not the norm. It is the exception, a brief, anomalous flicker in the history of a cosmos that will spend the overwhelming majority of its existence in cold, dark silence.